This figure shows how real-world operations feed data into the twin and how the twin produces recommendations. It highlights the feedback loop between execution and planning. The operational advantage is resilience. When demand changes or equipment availability shifts, the twin can reevaluate assignments and propose updates without starting from scratch. The architecture is a system of systems. It includes a physical asset twin for racks and equipment, a process twin for workflows, a performance twin for key performance indicators, and a predictive twin for forecasting. This separation matters because different subsystems update at different speeds. A robust digital twin needs consistent data synchronization and clear interfaces between these components. This slide reports a large-scale pharmaceutical distribution center example. The facility is 500,000 square feet and integrates 2,500 Internet of Things sensors, 50 automated guided vehicles, and 12 picking zones. It processes 15,000 real-time data points per minute and runs 50 parallel optimization scenarios every 15 minutes. These numbers illustrate what continuous optimization looks like in practice. During a flu season demand surge, the twin identifies a better configuration by repositioning antiviral medications. The reported change is 40% closer to pick stations. The reported benefit is an 18-minute reduction in fulfillment time per order, generating $2.3 million in annual savings while maintaining a 99.7% fill rate across 25,000 stock-keeping units. Tier 6 describes a distributed approach where locations and products are treated as agents. Location agents advertise capabilities and bid for products, while product agents evaluate offers based on multiple criteria. The key idea is that you can achieve emergent system-wide optimization without centralized control. This is especially valuable when the system is large and changing quickly. This figure illustrates the multi-agent negotiation framework. It shows how bids, proposals, and contract-like agreements can create stable assignments. The operational benefit is adaptability. If a location becomes unavailable or demand shifts, agents can renegotiate and reconfigure the layout without requiring a full, centralized reoptimization. The slide lists emergent behaviors such as seasonal migration, affinity clustering, load balancing, and adaptive resilience. These are patterns that arise from repeated negotiations. In practice, emergent behavior is valuable only if it is aligned with operational goals. That is why agent utility functions and governance constraints matter. This slide reports an e-commerce fulfillment center example with 100,000 stock-keeping units. It includes 500 location agents and 100,000 product agents negotiating assignments. During Black Friday preparation, high-velocity electronics migrate 35% closer to pick stations. The reported system reaches 92% of centralized optimal, reduces computation by 99.7%, and adapts 15 times faster. Tier 8 adds governance beyond pure cost. The idea is to prevent optimization from creating unfair, unsafe, or unsustainable outcomes, even if they look cost-efficient. This tier introduces ethical constraints, monitoring, and auditing mechanisms. The goal is to keep the optimization aligned with worker welfare, sustainability, and service equity. This figure shows an architecture for embedding ethical constraints into assignment decisions. It highlights how different stakeholder values can be formalized and monitored. A practical takeaway is that governance must be continuous. Without monitoring, models can drift over time and produce decisions that violate safety or equity goals. The slide lists concrete constraints. Workload equity limits so no worker exceeds 110% of average pick weight per shift, an environmental constraint targeting 15% lower energy consumption, and a service equity target within 2% parity across customer zip codes. It also reports a trade-off. Pure cost optimization yields $2.1 million savings, while the value-aligned approach yields $1.8 million savings, with a 23% increase in worker satisfaction and a 12% reduction in carbon footprint. These practice questions ask you to formulate and solve a small Tier 1 model with 5 products and 3 locations, including affinity relationships and a capacity of 2 products per location. They also ask you to implement the savings heuristic for 6 products and 4 locations, compute the savings matrix, and quantify percent improvement over individual placement. These questions ask you to design a moth flame optimization algorithm for 8 products and 5 locations with population 20 and iterations 50, plus an affinity distance rule of 2.0. They also ask you to design a variational autoencoder trained on 500 historical assignments, specify the architecture and loss, and evaluate on 50 test cases. These questions ask you to design a digital twin for a 200,000 square foot distribution center, including data inputs, synchronization frequency, and decision support interfaces. They also ask you to design a multi-agent negotiation protocol with 10 location agents and 25 high-velocity products. Simulate 100 negotiation rounds and analyze emergent patterns. This question asks you to implement a value-aligned storage assignment framework that balances cost efficiency with worker safety, energy consumption, and service equity. It also asks you to compare the value-aligned solution against pure cost optimization across multiple dimensions, so you can quantify the real trade-offs. SLAP is a high-impact problem because placement decisions shape every pick every day. Tier 1 gives a rigorous baseline and clarifies what feasibility and cost really mean. Tier 2 and Tier 3 provide scalable solution methods. Tier 4 adds learned priors from historical data, and Tier 5 and Tier 6 support continuous adaptation. Tier 8 ensures the system remains aligned with safety, sustainability, and fairness.